Okay, so let's recall the definition of a homomorphism. So we let x and y be topological spaces. And f from x to y a function. So we say f is a homomorphism if two things happen. So firstly, f is a bijection. So there is an inverse map. From y to x. And b, both f and f inverse are continuous. Okay, so the key point here is that this, in the second condition B, we really do need to specify that both f and f inverse are continuous. If just f is continuous, it doesn't automatically follow that f inverse is continuous as well. So let's just give a very basic example to illustrate that. So here, for this one, we're going to take y just to be the real line, but x is going to be part of the real line, going to consist of the union of this interval from -infinity to 0, closed at 0, union with the interval from 1 to infinity. Or, in other words, this is just R, except we remove the interval from 0 to 1. Okay, move this half open interval here. And then we just define f from x to y. So fx is just going to be an x if x is less than or equal to 0, and x minus 1 if x is bigger than 1. Okay, so of course these are the two parts of your space x, so this gives you a well-defined thing. And it's easy to see this is going to be a bijection with f inverse y is y if y is less than or equal to 0, and y plus 1 if y is strictly positive. Okay? It's easy to see that it's a bijection. But I want to claim that f is continuous and f inverse is not. Okay, let's just draw the picture first. Okay, so here's your x. X is like this. It consists of this is supposed to be our interval from -infinity to 0. I put a little bar there to indicate that 0 is included. I put a little circle, a little round bracket there to indicate that 1 is not included. So that's our that's going to be our space x, whereas our space y is just the real line, and the action of f is just sending all these points here to the same points, because by this first clause here that f of x is x when x is less than or equal to 0, and then x is just shifting everything here crosswards like so. Okay, so the effect of the map f is just to sort of connect these two things together. So how do we prove that f is continuous and f inverse is not? Well, a key point is to understand how we can describe these two parts here. So let's put u. This is going to be x intersect -infinity 1/2. I'll write it like that, which is just the same thing as -infinity, square bracket 0, right? Here, half is here, of course. So if we look at the part of x, which is less than a half, that's just this left part here. But the point about writing it this way is that this makes it clear that this is open in the subspace topology, right? Because we take this -infinity 1/2, that's open in the reals, intersect it with x. So that gives, by definition, is open within the set x. Okay, and v similarly is x intersect a half infinity, that's just the same thing as 1 infinity. Okay, so these are both open in X. Now, if you look at the map F, well, F is continuous on U and on V by sort of pretty obviously, because F is just the identity on U and just subtract 1 on V. So F is continuous on U and on V, and therefore on X by open patching. Okay, so that's enough to prove that F is continuous. But we also want to prove that F inverse is not continuous. So let's just make some space here. Okay, so we want to prove that F inverse is not continuous. So we'll have a look at now. Okay, so we've got F inverse is going from Y to X, and we've got this U is open in X. So for F inverse to be continuous, F inverse inverse U that should be open in Y. Okay? But F inverse inverse of U is just the same thing as F of U. Remember here I'm using this upper minus 1 in 2 different senses here. This second one means pre-image, this one means the inverse of the bijection, but it all kind of works out that there's just this, in the most obvious way, that this pre-image under the inverse function is just F of U. Okay? And F of U is just minus infinity 0, which is not open in Y. So F inverse is not continuous. Which is kind of obvious, reasonably intuitive if you think about this here. I mean, F inverse is sort of splitting the real line apart at this point. Half of it stays to the left, half of it goes to the right, and so there's a kind of discontinuous jump there. So that's our standard example of a continuous bijection that's not a homeomorphism.